All right, so if we look back to this idea of separation of variables, say for instance a problem like this, dx dy, or sorry, dy dx equals 2xy, where we require y to be greater than 0. We talked about solving this by separation of variables because that's possible because this right-hand side can be written as a factor that is only a function of x times a factor that is only a function of y, right? And to accomplish that, what we did, we talked about separating the variables, but really what we did was we multiplied in order to accomplish that, we multiplied by 1 over y, and then we moved the dx over as well. But when we multiplied by the 1 over y, we were then able to integrate both sides. 1 over y is what we call an integrating factor. An integrating factor is something that you can use. You can multiply both sides of a differential equation by, in accordance with our rules of solving equations, and as a result you end up being able to integrate both sides. Something to multiply both sides of the equation by so that you can integrate both sides and thus solve it. That's the definition of an integrating factor. All right, so now we want to start looking at, we're going to bump up in level of complexity. We're going to start looking at differential equations that look like this. This is the structure we're after. And these wouldn't necessarily, well, they wouldn't be solvable by separation of variables. So, we have to have a new technique. So what you're looking for is, of course, a first derivative, right? This is a first order linear differential equation. So the first derivative. Then we can have a term that has y in it, and its coefficient is a function of x or just a constant, but there's going to be a y term, and then we could even have a separate, completely separate from the dy dx term and the y term, a separate function of x term, right? So we could have a bunch of stuff here, but it's all x's, a bunch of stuff here, but it's all x's, and then this structure. All right. So if this is the differential equation that we've got, we can solve this by using an integrating factor. And what is the integrating factor we're going to use? Let's try that again. The integrating factor it looks like this. We'll call it rho. All right, rho of x. So it's a function of x. Doesn't really matter what we call it. Here it is. E raised to the integral of p of x dx. E raised to the integral of p of x dx. So we've got to find the integral of p of x and then exponentiate it. And then that's our integrating factor. Okay, so let's see how that works when we use that particular integrating factor. Of course, what we're going to do is we're going to take our differential equation. Let's just put it right here. Dy dx plus p of x y, and we're going to multiply that by e raised to the integral of p of x dx. Okay. That's the left-hand side, equals q of x, and we're multiplying it by the same thing, e raised to the integral of p of x dx. Remember, our goal is to solve this. Our goal is to ultimately be able to, ideally we'd love to be able to get a solution y equals some function of x. But at the very least, we want to get rid of the all integration signs and just have maybe even just an implicit function. All right, so let's do a little work here. Just a little tiny bit of algebra here. This is no big deal. We just distribute this through. And of course this right hand side stays where it's at. Q of x. Okay. Now it looks like we've made a big mess of this thing. Okay. Looks like we've made things way more complicated. But here's the tricky part. I'm going to take a little bit of an aside here, right? So we're going to, well, this is kind of a little aside. I want you to imagine differentiating something that looks like this. Find the derivative. Now let's do it like this. Let's do it like this. Let's find the derivative. So this is just an aside. We're taking a little pause here. I want you to find the derivative of a term that looks like this. Y of x times e to the integral of p x. So imagine somebody came up to you on the street and said, hey, what's the derivative of y times e raised to the integral of px? Of course, you're going to apply the product rule, right? So you're going to take the derivative of the first thing, derivative of y of x, so dy dx, times, we'll change times e to the integral of px dx, plus, now you take the derivative of the second term of the second factor, that one right there, and of course we know how to differentiate exponential functions. We're going to get a copy, e to the integral px dx. Now we got to take the derivative of this using the chain rule, right? And of course the derivative of an integral is just the integrand. So that's the derivative of the first times y of x. Okay. So if we differentiate this, then we end up with this expression. So likewise, if I let's write this here. So as I was saying, likewise, because if I differentiate this thing, I get this. That means that if I integrate this, I should get this, right? That's the relationship between derivatives and integrals. Let me say that one more time. If you differentiate this, you get this. That means that if you integrate this, you get this. Okay. All right, so that's our little aside. Let's talk about why we made that aside, and you probably already see that. Notice, this term right here is sitting right there, right? E to the integral px dy dx times px e to the integral y. It's all there. Okay, so remember what I said? If I differentiate this, I get this. That means that if I integrate this, I get this. So what that means is if I integrate this right here, I get this right here. Okay? So here's the reason we use this integral, this integrating factor. Because now I can integrate this and get this. Okay? And in fact, that's the next step in the process. And all this commentary is making it look more complicated than it really is, because when you integrate this left-hand side, well, actually, we're working on the entire equation here, so we got to integrate both sides, right? Which is, kind of what we do. The integral of e to the integral of p of x dx dy dx plus e to the integral of px dx px y equals the integral of, and we're doing the dx, the integral of the right hand side, which is e raised to the integral of p of x dx q of x dx, right? And look what happens. This left hand side simply becomes this, y of x times e to the integral of p of x dx. And the left hand, or that's the left hand side. The right hand side is what it is right here. Okay. And we have found a solution to the differential equation. Okay. Provided, of course, that we can find this integral, right? You got to be able to evaluate that integral so that you just have e raised to some function of x right there as well. And we can do that integral. If you can do that, then we now have a solution to the differential equation. Because look, we've got our y sitting right there. We were able to get rid of our dy dx's, right? Okay, so that's the process. So we actually streamline it a little bit more, realizing that once you introduce the integrating factor here, you can just integrate and integrate, and the left hand side is always going to be that, the right hand side is always going to be that. So we'll integrate, and then just kind of jump right down there, knowing that all of this stuff happens. All right, so let's see that once in action and see how we can use this to solve a differential equation. All right, so here we go. Here's a differential equation. It's actually an initial value problem, of course, because we've got that initial condition that we need to solve for. All right, and so once I recognize that it fits my pattern, right, then I'm going to know I'm going to use an integrating factor, right? I got my y prime. I've got something times y, okay, and that something is a -2. Okay, that's important because that something is what gets used as the as p of x, right? And then equals some function of x. So if I'm going to solve this, the first thing I'm going to do is find the integrating factor rho, which is just e raised to the integral of -2 dx, right? I just have to integrate p of x. So just doing that real quick, that's going to be e to the -2x. And we don't worry about the plus c for the integrating factor. All right. So once I've got that in place, I'm going to multiply both sides of my integral, or my differential equation, by that integrating factor. Right? Just multiply both sides. And then I can immediately just integrate. Okay? Now here's the nice thing that we always know, right? Once I integrate that left-hand side, as we mentioned, it is simply going to be y of x times e to the -2x, right? I don't have to go through the actual integration process because I know it fits the pattern. That's why we chose this integrating factor. If you're not comfortable with that, you can, well, I would say you could actually expand it out, but really even when you expand it out, you have to, all you're left with is recognizing that the integral of something that complicated just becomes that because of this idea. So we just save ourselves some headache by just realizing, thanks to that integrating factor, the left hand side is always going to be y of x times that integrating factor. Now the right hand side is still the integral of e to the -2x times 3 e to the 2x, but hey, look, once we simplify that, that's dx, by the way, Once we simplify that, that's just going to be a 3 dx, right? And that's super simple. Y of x equals e to the negative 2x, or times e to the negative 2x, equals 3x. And now we put our plus c in there because there's where the plus c is. And now if I want to solve for y, I'm going to multiply both sides by e to the 2x. And that gives me y of x equals 3 e to the 2x, 3x e to the 2x, that's better, 3x e to the 2x plus c e to the 2x, right? There's my solution. Y equals some function of x. Now I just need to apply real quickly apply my initial condition, which is 0, 0. So if let's just work that right over here, right? So if I plug in 0 in for all the x's, I better get 0 out. Let's see, this is 3 times 0, so that first term turns into 0. The second term turns into c, so it looks like c equals 0. C must equal 0. So our official final solution is y of x equals 3x e to the 2x. Bam, there it is. All right.